It is the middle of July. The outside temperature is 94 degrees. Inside the house, the air conditioner has been running for 6 hours straight. The electric meter is spinning. The monthly bill is climbing. And somewhere under that same house, 6 feet down in the earth, the ground temperature is sitting at 55 degrees. It has been sitting at 55 degrees since February. It will still be 55 degrees in October. The house is burning energy to create cold. The cold already exists beneath it. A central air conditioning system capable of cooling an average American house costs between $5,000 and $15,000 installed. It consumes between 2 and 5 kilowatt hours of electricity for every hour it runs. In a hot summer, it runs for 8 to 12 hours a day. The monthly electric bill during cooling season reflects every one of those hours. The system works, but it works by continuously purchasing energy to move heat from inside to outside. Stop paying the bill, and the cooling stops. But the physics of cooling do not require a compressor or a refrigerant circuit. They require a temperature difference and a path for heat to travel along that difference. The ground beneath every house in America maintains a natural temperature difference that costs nothing to sustain, requires no electricity to maintain, and sits at roughly the same temperature every summer as every winter. It is a thermal resource that has been present under every building that has ever been built. The question is whether there is a path connecting it to the living space above. The Earth below the frost line, generally 6 to 10 feet down across most of the continental United States, holds a nearly constant temperature year-round. Across much of the American Midwest and South, that temperature falls between 50 and 58 degrees Fahrenheit, regardless of whether it is January or July above. The summer air can be 94 degrees. The Earth 6 feet down is 55. That 39-degree gap does not require any equipment to exist. It exists because the sun cannot heat the Earth as fast as the Earth's own mass absorbs and averages the seasonal temperature swings above it. On some old farms that operated before mechanical air conditioning became standard, that underground temperature was already being used. Not through a compressor, through a pipe. A length of buried pipe running from an inlet outside the building down into the earth, along a buried horizontal section, and back up into the living space, or the barn interior. Hot outside air entered one end. By the time it traveled through the buried section, the surrounding earth had pulled heat out of it. The air arriving inside was noticeably cooler than the air that had entered outside. The principle is simple. Moving air in contact with a cooler surface loses heat to that surface. The rate of heat transfer depends on 3 things: the temperature difference between the air and the surface, the area of contact between them, and how long the air stays in contact. A buried pipe at 55 degrees with 90-degree summer air moving slowly through it is continuously transferring heat from the air into the surrounding earth. The earth absorbs that heat. The air arrives cooler. The earth does not warm up noticeably because its thermal mass is enormous compared to the amount of heat a pipe delivers to it. How much cooling is realistic? Under reasonable conditions, appropriate pipe length, correct depth, good soil moisture, and a modest airflow rate, the temperature drop from pipe inlet to pipe outlet can reach 15 to 25 degrees Fahrenheit. 94-degree outside air arriving inside at 68 to 75 degrees, not the blast of a window air conditioner. But combined with ceiling fans, window shading, and good insulation, enough to make a summer room genuinely comfortable without a single watt of compressor power running continuously for 8 hours a day. This type of system is called a ground-to-air heat exchanger, or earth tube in modern passive building circles. But the principle is not modern. Civilizations in hot, dry climates were moving air through underground passages to cool it long before electricity existed. Persian windcatcher towers drew hot surface air down into underground channels and delivered it into buildings already cooled by contact with the earth. The physics running through those ancient channels and the physics running through a modern buried drainage pipe are identical. The material changed. The principle never did. In American rural building history, the same principle appeared quietly in several forms. Old farmhouses across the South and Midwest were frequently built with basement ventilation passages, simple inlets in the foundation connected to a short buried run that allowed cooler underground air to enter and create a natural upward draft through the house. The farmhouse breathed through the earth. And every root cellar that every serious old farm had built was operating on exactly the same thermal logic. Dig below the frost line, enclose the space, and the ground temperature maintains a cool environment year-round at zero operating cost. Here is what ended the widespread practical use of passive earth cooling in American homes. Not a technical failure, not a safety concern. The arrival of mechanical air conditioning. A technology so immediately effective at producing cool air on demand that the slower, quieter, always available cooling from the earth simply stopped being relevant as a primary comfort strategy. When you can set a thermostat to 68 degrees in 30 seconds, 55-degree ground temperature starts to look like a consolation prize. The electric bill attached to that thermostat setting was a consequence that arrived gradually, then expensively. The cost comparison deserves a specific number. A central air conditioning system installed in a new home, $5,000 to $15,000 upfront, $800 to $2,000 per year in operating cost in a hot climate. Over 10 years, that is between $13,000 and $35,000 to stay cool. A buried earth tube system using corrugated HDPE drainage pipe. The black, flexible pipe sold at any farm supply or hardware store runs between $20 and $80 in pipe material for a functional installation. The ground does the rest for free every summer, without a monthly account. But here is the part of this system that most descriptions skip past. And it is the part that determines whether a buried pipe delivers cool, clean air or something considerably less pleasant. Air moving through a cool underground pipe does not just lose heat, it also loses moisture. As warm air cools, its capacity to hold water vapor drops. That moisture has to go somewhere. In a poorly positioned system, it condenses on the pipe walls, pools at low points in the pipe run, and creates exactly the dark, damp, still environment where air quality problems develop. The condensation challenge is not a reason to avoid the system. It is the engineering variable that determines whether the system works well or does not. The solution old builders arrived at through observation was simple geometry. A pipe that slopes consistently downward from its outside inlet toward a low drain point inside, or toward an exterior drainage outlet, moves condensed water continuously toward a place where it can exit or evaporate. It never pools. A pipe with flat sections, or worse, with low points where the slope reverses, pools water. Builders who noticed their ventilation inlets staying fresh year after year consistently had pipes that drained. The ones who developed problems consistently had pipes that did not. No engineering degree required to figure that out, just observation over time. There is a second consideration that anyone thinking about an earth tube system needs to address before any pipe goes in the ground. In certain geological areas, radon, a naturally occurring radioactive gas, is present in soil and groundwater at elevated concentrations. A buried ventilation pipe drawing air through those soils can carry elevated radon into a living space if the system is not designed to account for it. A radon test of the soil and air at the proposed installation site is a necessary first step. This is not a reason to abandon the idea. It is the reason a qualified professional familiar with local soil conditions and building codes should be part of any real installation decision. Pipe diameter is the variable that most affects how much cooling the system delivers. A wider pipe moves the same volume of air at lower velocity. Lower velocity means the air spends more time in contact with the cooler pipe walls and surrounding earth. More contact time means more heat transfer, which means a larger temperature drop at the outlet. A 4-inch pipe moves air through quickly with modest cooling. A 6 or 8-inch pipe at the same airflow rate keeps the air in contact with the earth longer and delivers a meaningfully larger temperature drop. The old farm ventilation passages that worked best were almost always larger in cross-section than the minimum needed for airflow. Pipe length is the other primary variable. A short run of 10 or 15 feet through cool earth produces a modest temperature drop. A longer run of 30 to 50 feet through consistently cool soil at consistent depth produces a much larger one. Old farm ventilation passages that ran under an entire barn floor or along a root cellar wall often achieved the longer contact lengths that produced the most noticeable cooling. The practical limit is that beyond a certain length, natural convection may not be strong enough to move air through the pipe without some mechanical assistance. That assistance, when needed, is a small, low-wattage inline fan, not a compressor. How does the air move through the pipe? In passive systems, the driving force is the temperature and pressure difference between inside and outside. On summer evenings, when outside air cools slightly and inside air remains warm from the day, natural convection can draw cooler outside air through the buried pipe into the house. During peak daytime heat, when outside air is hotter than inside, the natural drive reverses and the system needs a small fan to maintain the correct flow direction. A 3-watt computer fan or a small DC fan Connected to a solar panel small enough to fit in a shirt pocket is enough to maintain consistent flow direction without adding any meaningful electricity cost to the system. What a single earth tube can realistically provide in a well-insulated house on a 90-degree day is meaningful, but honest. One properly designed buried pipe run at correct depth and length can deliver a continuous supply of air 15 to 25 degrees cooler than outside temperature into a room. It will not match a 12,000 BTU window air conditioner, but it substantially reduces the hours that a mechanical system needs to run. Or in mild climates or well-shaded houses, it can handle the entire cooling load on all but the most extreme summer days. The variable that matters most is the specific climate and the specific house. The system works best in specific conditions. Hot, dry climates with cool soil. Much of the American Midwest, the Great Plains, and parts of the Southwest offer ideal conditions. Dry air holds less moisture and the condensation challenge is smaller. In very humid climates, the condensation management becomes more demanding, and the system needs careful drainage design. In areas where the water table is very high, burial at the required depth may not be feasible without encountering groundwater. The principle is consistent and real. Whether it applies cleanly to a specific property depends on the specific ground conditions under that property. Old builders who incorporated earth ventilation into their farmhouses and root cellars were not applying the vocabulary of modern passive building science. They were solving a practical problem with available materials and observation. They noticed that certain rooms stayed cool all summer without any effort. They noticed that the root cellar never needed ice to stay cold. They noticed that the basement air on a hot afternoon was the most comfortable air in the entire building. And some of them followed that observation to its logical conclusion. If the Earth is producing cool air below, the next question is how to bring more of it upstairs.
Modern passive house construction has formalized exactly this principle under the engineering name ground-to-air heat exchanger. High-performance homes in Germany, Scandinavia, and increasingly in the United States include earth tube systems as standard elements of their ventilation design. They are measured, tested, and documented in building science literature. Their cooling contribution in those certified buildings is consistent with what old farm builders observed informally over generations. Real, free after installation, and available every summer without a running meter. The physics that old farmers noticed in their cellars is now a line item in Passive House certification specifications. What was actually lost when mechanical air conditioning made passive earth cooling invisible was not the technique. The technique is simple enough to implement with a shovel and $50 a drainage pipe and a free afternoon. What was lost was the habit of treating the ground beneath the building as a thermal resource, a stable, free, continuously available temperature reservoir that every building in every climate sits on top of and that most homeowners have never been told to think about. The monthly electric bill is a very effective way of preventing that thought from forming. The ground temperature under your property right now is probably somewhere between 48 and 60 degrees Fahrenheit, depending on your latitude and local soil conditions. It has been in that range all winter. It will be in that range all summer. Your air conditioner is burning between $800 and $2,000 a year to produce a temperature that already exists 6 feet below your foundation. The question that old farm builders asked when they designed their root cellar ventilation passages was not a complicated engineering question. It was the simplest possible question. How do I connect what I need to where it already exists? Leave a comment telling us your situation. Do you have a basement, a crawl space, or bare slab foundation? Do you heat with a wood stove or another fuel? Have you ever noticed that the air near your basement floor in summer is noticeably cooler than the rest of the house? That temperature difference is the same earth cooling effect at a small scale. Tell us what your property looks like and whether an earth tube approach fits what you are working with. Every answer helps this channel understand what problems the next investigation should address.